Hello everybody, and welcome back to another CIV E 398 assignment tutorial. Now in this assignment tutorial, we're going to be covering assignment 4, question number 2, which deals with strain in 3 dimensions. So we're starting to deal with strain tensors or strain matrices. It's not as simple as the uniaxial strain measures we saw in the previous question. This is when shit gets real, if you will. So question 2 says a cube undergoes a deformation such that the infinitesimal strain matrix, or the small strain matrix, is described as such. And we have a nice 3x3 matrix, nothing too special. Some notes that we need to talk about the small strain matrix. As we can see, it is symmetric, and that'll help us a lot when dealing with question D. But what the question wants in general says, part A, it wants us to find the principal strains and their directions. Part B says the longitudinal strain along the direction of vector dx. C, which says the approximate change in the angles between vectors dx and dy. And then finally D, the coordinate transformation matrix Q that transforms E small into a diagonal matrix. And just by looking at part D here, you guys will say, oh wait, diagonal matrix, symmetric matrix, ooh, this sounds familiar. And as you guys will see, that's a nice easy question because you guys are already such experts. All right, so let's talk about the first question, which is principal strains and directions. So as you guys will see, the term principal will appear quite frequently in this course because not only does it apply to strains, it also applies to stresses. And you're saying, okay, Clayton, well, principal strains, principal stresses, what exactly does that mean? Well, the principal strains are the eigenvalues of the strain matrix. And as you guys will see later on, the principal stresses are the eigenvalues of the stress matrix. So whenever you guys see principal, eigenvalues should be associated with it in your head. Principal strains, okay, it wants the eigenvalues. Or if we want principal directions, those must be the eigenvectors of the strain matrix. So again, you guys ever see principal, the word principal at all, you guys should automatically be thinking about the eigenvalues and the eigenvectors. So question now becomes all right, well, how do we calculate this? Well, I'm going to go through the exact same slides as the previous last 3 seminars. I switched it up to include the strain matrix directly, but again, this should all be reviewed to you guys. This is why we cover eigenvalues and eigenvectors, because they play such an important role in everything else that we do. So quick review, to determine principal strains, which I called lambda, we need to solve the equation, the determinant of the strain matrix minus lambda I is equal to 0. So if we want to do it by hand, we just define our strain matrix, and then we can go the strain minus lambda I, the determinant of that is equal to 0. We get a nice long equation. However, there is some simplifications we can do to solve this cubic equation, because again, since it's cubic, we can solve for the 3 principal strains. So, moving forward, we can simplify because in all your guys' questions, E1, 2 and E1, 3 is equal to 0. And since the strain matrix itself is symmetric, we know that E2, 1 and E3, 1 are also going to be 0. So that simplifies everything really nicely into one equation. From here, we can very simply solve for all 3 of the cubic roots, just by switching this into the quadratic formula. As you guys can see, we have 3 unknowns that we can easily solve for. Now, option 2, which is what you guys are using, this is why I kind of went through it really fast. Mathematica, we can define our strain matrix as M, and we just simply type in eigenvalues of M. And by now, you guys are the kings and queens of Mathematica. No explanation needed for how to do that. Similarly, we can go, oops, I forgot a quick little note. So yes, remember that the assignment requests the eigenvalues to be input in ascending order. You guys did really good last time. I got no questions, but I wanted to leave this in here in case you guys forgot. So ascending order, but again, you guys were so great last assignment. You guys are just laughing at me saying, we know Clayton, shut up and move on. So let's move on. So principal directions, again, these are just going to be the eigenvectors of the system. So to do that, we need to solve the equation where the small strain matrix times a vector p is equal to lambda p, where lambda is those eigenvalues we found before. So if we expand it out, we have the small strain matrix multiplied by a vector p1, p2, p3, which is equal to lambda p1, p2, p3. And again, we know all of the strain matrix entries, we know all the lambdas, so therefore our only unknown here is actually p1, p2, and p3. So this creates three equations, which is great because we have three equations. We have three unknowns, which are P1, P2, P3. So we can solve them, but as you guys remember again, of course, this will have infinite solutions. So what we need to do is we need to assume a value of P1, P2, or P3. I personally pick P3 is equal to 1, and then we can solve the equation. How do we do that? Well, if I assume P3 is equal to 1, I can look at the first two equations. I have two equations, two unknowns, so I can solve for P1 and P2. And then I can say that my eigenvector P is P1, P2, which I just solved for, and then finally 1. And then the last little note, of course, this is not normalized. Usually you will have to normalize them when dealing with symmetric matrices because we want that orthogonal transformation matrix Q. So again, just a little heads up that this is not normalized. And finally, we repeat this with the remaining principal strains. So remember that we have three eigenvalues. We have three different values of principal strains. We need to repeat this process for each one. But of course, you guys are going to use Mathematica. Why wouldn't you? So to do that, all we have to do is define our strain matrix, but we already previously did that. So all we need to really do is type in eigenvectors of M or eigenvectors of E, whatever you define your matrix as, and you're good to go. Nice and simple. So now let's talk about the actual new stuff, the longitudinal strain in a direction. So knowing the small strain matrix, which we do, the longitudinal strain along a vector dx can be calculated using the following formula. Now, when I first saw this, I kind of shit my pants a little because it's like, oh my god, dx, integration, derivatives, what does that mean? The key here is realizing that that dx that appears 3 times in this equation is just a vector. It's not a differential, there's no calculus involved at all, it's just simply a vector. And as we remember from our question, I believe our dx is 1, 1, 1, or you guys may have something different, but dx is just a vector. And now that we know that dx is just a vector, we can look through this equation and try and figure out what exactly the result should be. So if we look at this term here, where we're taking our small strain matrix and just multiplying it by dx, well, that'll just turn into a vector. Okay, well that's not too bad. Well then if we look at the top of the whole, we have dx dotted, so remember that's a dot product, that's not just multiplication, dotted with e dx. Well, that should just be a scalar value. I'm dotting two vectors together. That's just going to end up with a nice scalar value. And finally, at the bottom, we have the norm of dx squared. Well, the norm of dx is going to be just a number. Square that. Well, that's still going to be a number. So this whole equation, we're going to have a number on the top, a single number, divided by a single number on the bottom. So the strain along the direction dx should just be a number in the end. It should be a scalar value. Nice and easy. So again, the key here to me was just realizing that that dx there, that's just a vector. It's not a crazy differential or anything like that. So now the second part of the question, or I guess part C, it gets a little bit more complicated. It wants the change in angles between two vectors. So we're given this formula where cosine of theta f minus cosine of theta I divided by 2 is equal to everything on that right side. And we discussed everything on that right side, so it wasn't too complicated. We see that that right side will just turn into basically a number. The only difference before is instead of just using dx, we have dx and dy now. So remember, dx and dy, they're just vectors. I put a smiley face here because they're nice, happy vectors. They're nothing to really be scared of. There's no differential, there's no calculus, nothing like that. They're just straight up vectors. So if we look at this formula now, we can say, okay, well, dx, dy, I know that. The small strain matrix, I know that. My only unknowns are theta f and theta I. Well, theta I is the angle before the deformation, and theta f is the angle after that deformation. So theoretically, if we know the angle before the deformation, theta I, we can use the equation above to solve for the angle after deformation, theta f. So to say, okay, Clayton, well, that doesn't seem too bad. I can solve for theta f if I know theta I. Well, how do I find theta I? Well, the angle before deformation can be found using the dot product. So this goes back to your Eng 130 days where we're finding the angle between two vectors. There's a nice simple dot product formulation where it's dx dot dy is equal to the norm of dx times the norm of dy times cosine of theta I. And so if we look at this formula closely, it's reliant on three things. The components of dx, which we know, the components of dy, which we also know, and theta I. And if we look at this, we say, okay, well, theta I is actually our only unknown in this scenario. So I can use that formula to solve for theta I, no problem at all. And since we now know theta I, we can use the formula in the previous slide to find theta F. And then simply the change in angle will just be theta F minus theta I. So all we have to do is use the dot product to find theta I, use the previous formula to find theta F, and then we subtract theta F from, we take theta F and we subtract theta I. So hopefully that makes a little bit more sense. Again, dx, dy, they're just vectors. Like I said, I got scared when I first saw them, but you guys shouldn't be. All right, so the final one is wanting to find that coordinate transformation matrix that turns the small strain matrix into a diagonal matrix. So again, it's a symmetric matrix, which makes this question nice and easy, because recall that if the eigenvectors, which I labeled as P, Q, and R, of a symmetric matrix M are used as the coordinate transformation matrix Q, the result will be a diagonal matrix, which I put E small prime. So at the very top there, I put symmetric matrix M. That should be symmetric matrix E. So what does this mean? I don't like English. I prefer actual equations. Well, this means that if I want E small prime in diagonal form, we can make it equal to Q times E small times Q transpose. And the key here is that Q will have the rows of the eigenvectors. So if we look at the first row of Q, it's P1, P2, P3. Look at the second row of Q, it's Q1, Q2, Q3. And the third row of Q, that's R1, R2, and R3. Well, then if we take that matrix and transform E small, then E small prime is just going to be a nice diagonal matrix consisting of the eigenvalues or the principal strains. So the key here, which is what I kind of talked about before, is that it's very important that Q is an orthogonal matrix. Remember that coordinate transformation matrix has to be orthogonal. Well, why is this important? What does this mean? It means that all those eigenvectors that you found, they have to be normalized when throwing them into Q. If you throw unnormalized eigenvectors into Q, you won't get the right answer. So it's very important that you normalize your eigenvectors before throwing them into Q. And with that being said, that concludes this question. It's a little bit longer. The next question is probably pretty long too, but after that, it's pretty easy. So thank you guys so much for listening. I will see you guys in question number 3.